Hey and welcome. Today we will solve intersection of two linked lists interview question which mostly asked by Apple as well as some other companies like so. We will explore two solutions for this problem, so without further ado, let's dive in. Here is first example. As you can see, we have two linked lists A and B. First one, A, is shorter than second one and they intersect at node 8. We need to find that intersection node and return it. Second example, and same story, but this time linked list B is shorter and they intersect at node 2. And finally, in last example, they don't intersect at all and we might return null for it. Let's see how we are going to solve this problem. In order to solve this problem, in a very high level thinking, we need to iterate over both of linked lists to know which value every node has. There's no direct access point for linked list. We can say that give me the value at this point or this one from this specific index, like arrays. We need to know which nodes exist inside of the linked list first to match and compare them together and find the intersect point. So two traversals we need for both linked lists. But for finding the actual intersection point, we cannot say that we could iterate over both linked lists at the same time and when we reach into the node with the same value, declare that we found the intersection point. Because there's no guarantee that those linked lists has the equal length, right? As we saw it in the examples. That is our main problem here, but still there is a way for us. What if in our first iteration, with help of some sort of storage, we keep track of nodes in one of the linked lists. By doing so, when we iterating over our second linked list, we can check each node, and as soon as we find one node that exists inside of our hash map, then we would know that node is the exact intersection point because we found it in both linked lists. But there's a bottleneck with this solution, and that is our hash map. Think about a scenario like, what if we don't know which linked list has less nodes and pick the longer one and store every nodes of it inside of our hash map? And let's make it even worse than that. What if this longer linked list has millions of nodes inside of it, and at the very worst case, both linked lists does not even intersect at all? Now you might know where I'm going with this. Our hash map will take lots of space in that case, and a better solution would be to get rid of it because of a memory consumption. We are going to upgrade our strategy. There's an idea about balancing both linked lists. Let's see how will that work. The idea is we know that these two linked lists are not equal in size. If we can make these two linked lists equal in size, then we can easily start iterating from very beginning node and compare both nodes at the same time. This was our high level idea from beginning, right? But how? What we can do is that we can put shorter one in front of longer one and the other way around, put longer one in front of shorter one. By doing so, no matter what, we will have two equally sized linked lists. Now, if we start to iterate over each of those, at some point, we will reach into a node that has the same value. And more importantly, we will not going to need to keep track of node values from either of those linked lists, which would mean no extra space occupied anymore. Simple, but really elegant. Let's write code for both solutions now. So here we are in leetcode. For Hashmap solution, first we need to define our map object. The point behind defining a map object instead of simple object is that map supports entire objects as key, and that means we can store our nodes as a key. Also, one other advantage is that with objects, we need to store the values of nodes as a key, but we are not 100% sure that values in linked lists are going to be unique. Then we will iterate through any of those linked lists. Since we don't know which one has less nodes, we will pick first one and then iterate through that. Also, we will attach first linked list heading to temp variable for our iteration. So as long as HA is a true C value, we need to do some stuff. Inside of our iteration, we are going to update our hash map with every node value until we reach into the end of our linked list. Now it's time for our iteration over second linked list. It will be quite like same before. But this time, inside of our while loop, we will first do or check to see if the node we currently have in our hands exists in our hash map. Because if that is the case, then we found the intersection point. And otherwise, we need to keep looking for other nodes. At the end, if we haven't found any intersection point, we can return null. Now, if I run this, test should be passing, and if I submit, everything should be fine. But as I said, we are using space here with our hash map. So let's get rid of that space consumption. For that, code will be simple. First, I will put the same visualizations we saw in the slides here as a comment for reference. And with that, we are going to initialize our basic pointers for iteration over both of linked lists. Now the while loop condition is going to be a bit different here. We are going to check that as long as if two pointers are not equal to each other, and as long as that is true, we need to check if we are at the end of linked list A, then we might attach linked list B, and if not, we might continue the iteration on that linked list. And exactly the same for other linked lists too. If we have reached into the end of it, it, we will attach linked list A into tail of it. Otherwise, we will continue our iteration. At the end, we will exit this while loop whenever both nodes are same, right? That was our condition, and we can simply return either of them because they are equal. Now, if I run this, test cases are passing, and if I submit, we are in a good shape here without using any space. Now let's jump into slides for time and space complexity analysis. For time complexity, we will have O of n plus m for both solutions because we will iterate through both linked lists, and worst case could be there is no intersection point between two linked lists, which would mean iterating through every node in both linked lists. For space complexity, it is going to be O of n for Hashmap solution and constant O of 1 for balancing linked list solution. So that was it for this video. I'll put link for my linked list playlist in the description to check it out. Thanks for watching, and please leave a like, comment, and subscribe to the channel. And finally, hope you enjoyed this video and stay tuned for the next one.